In this video, we're going to start talking about conservation of energy. The first thing we want to do is we want to compute the work done by a vector field along a path, so a particle traveling along a path. So let's say, we'll just set up the problem here. Let's say we have a couple of points in space, and we have a path, so a particle traveling along a path. The path doesn't have to be remarkable, but a particle traveling along a path from A to B. And along this path, there's a vector field that is doing some work on our particle. Okay, and so we've got this vector field F. And remember, in a previous video, we've worked out a formula that the work done by a vector field along or on a particle is equal to the path integral. So it's equal to the integral along C of F dot dr. Now, we are going to invoke some facts from physics here, which if you haven't taken physics, you'll just have to take my word for it. But if you have, I think this example is going to enlighten or elucidate some things here for us. So the first thing is Newton's second law. So Newton's second law says that any force, by the way, this path, so I'm about to say something that's going to require us to have some kind of parameterization of the position of the particle along the path. So we'll say that this path is given by some vector function r of t. And so Newton's second law, now that I've done this, says that force is always equal to mass times acceleration. Our particle, we're going to assume, has constant mass, and we might remember from either physics or calculus 1 or 2 that acceleration is the second derivative of our r dot. Really, we should remember this from earlier in Calc 3, right? So what we have then is that F is equal to mass times r double dot, the second derivative. All right. The other fact from physics that we're going to use is that the kinetic energy of a particle, so the kinetic energy of a particle is given by this function k, which is a function of time. So kinetic energy is changing as the particle moves along this path. And kinetic energy is given by 1/2 mv squared. Now this v is actually not velocity. This v represents speed. Okay, v represents speed here. So another way to write this is that this is 1/2 m times the magnitude of the vector v of t. Squared. Okay, but the vector v is the first derivative. This vector v is the velocity, and the velocity vector is the first derivative of position. So it's not r double dot, but it's r dot. And so our kinetic energy function is 1/2 times mass times the length of r dot of t squared. Okay, and again, so this is our function k of t. And again, what we have learned in calculus 2, this r dot is representative of speed, and of course v is the symbol for speed in physics. We've used ds dt to represent our speed. We never really called it v, but that's okay. So we'll call this lowercase v, not in vector form. That's the key here. It's not a vector. It's a scalar function. Okay, so what we want to do is compute the work, and the idea is to show that the work is related to the kinetic energy. So I'll just write over here. But we know that our work is the integral, path integral along the path of f dot dr, okay, on one hand. On the other hand, what do we know? F is given by this. So before I write this down, let's recall that dr is r dot times dt, if we're working with t here. And in terms of our parameterization, let's assume that our initial point, r of a, corresponds to time t equal to little a, and r of b corresponds to r of little b. The usual choices here, so that we can rewrite this entire integral in terms of t and r dot, r double dot, etc. What we end up with then is that the work is equal to the integral from a to b of the force we're going to replace by this formula. So it's m times r double dot, but that's the vector field, right? That has to be dot product with our dr. Our dr is r dot dt. R dot dt, okay? And so this mass is constant. It can come out. Now in relativity, mass is not constant, but that's okay. We're not doing relativity, all right? We're doing Newtonian physics. And so we can then rewrite this entire integral like this. So anytime you take a dot product of two vector functions, you end up with a scalar function. This integral makes perfect sense. Other than the way that it's written, it's probably a perfectly fine Calc 1 or Calc 2 integral. But let's take advantage of some other facts that we know. And you may remember from way back near the beginning of our study. So I'll write recall here. By this I mean our study of entire Calc 3, so back when we studied vector functions, that if you take the dot product of two functions, all right, and then you take their derivative, then the product rule has to apply to this, right? So I'm taking the derivative of r dot with r dot. Why? Well, we're going to see, but the derivative has to obey a product rule here in terms of the dot product, and so the derivative adds a derivative to the first term and leaves the second alone. Then it leaves the first alone, adds one to the second term, right? And remember, the dot product is commutative, so this is just 2r, well, let's do it this way, 2r dot, r double dot, dotted with r dot, okay? And that's exactly what we have here, right? And so what we can do is replace this dot product here with not quite this one, because we have this 2, right? But by 1/2 of this. And so what we have now is that our work is equal to, our m is still hanging out in front. I'm going to put that 2 out in front as well, this 2 that we have to divide through, integral from a to b of the derivative of r dot dotted with itself dt. And at this point you're probably remembering, and now you start to see, okay, we start to see where we're heading. Look at this over here. There's a 1/2 m, there's something involving r dot. That's our kinetic energy, right? And at this point, if you haven't already remembered, you should hopefully be thinking, all right, Justin, this r dot dotted with itself, that's exactly the length of r dot squared, right? And so we can replace it by that and write this as m over 2 integral from a to b of the derivative of, getting carried away here, the length of r dot squared dt. And at this point, fundamental theorem of calculus part 2 applies, right? The fundamental theorem of calculus applies. This is a Calc 1 or Calc 2 integral. The integral cancels the derivative. Now we just plug in the boundary points, and what we have is that our work is going to be equal to 1/2 m times the length of r dot of t squared evaluated at these two endpoints. Okay? Comparing with what we have here, that's just the kinetic energy at these endpoints, right? So this is k of r of b minus k, kinetic energy, at r of a, which is, of course, k of b minus k of a. So the kinetic energy at the terminal point minus the kinetic energy at the initial point. And so those of you who've taken physics might know, might recognize this, right, as the saying that kinetic energy, the work done by a vector field is just the change in kinetic energy from the terminal point to the initial point of that vector field, or of that particle.